como siempre. Es un placer para nosotros y un orgullo que vengáis a todas nuestras actividades. Bueno, antes de presentar a nuestro, iba a decir a nuestro intérprete, también a nuestro científico de hoy, quería comentaros un poco. Madrid tiene la gran suerte de tener a 30 kilómetros aproximadamente el Centro Europeo de Astronomía de la Agencia Espacial Europea, que se llama ESAC, le llaman ESAC, ¿no? European Space Agency Center, ¿no? Y Marcus KISSLER-PATIG, que es precisamente nuestro conferenciante de hoy, es el jefe de ciencia de operaciones de la Agencia Espacial Europea, que está en particular ocupado de toda la operación de heliociencia, de ciencias planetarias y de astrofísica de todas las misiones de la Agencia Espacial Europea. Hemos tenido la suerte de que haya aceptado nuestra invitación y él, bueno, pues tiene un currículum muy extenso que podéis ver en toda la información que os he enviado. Él actualmente trabaja aquí, pero ha trabajado en otras instituciones como en el ESO, en el Observatorio Europeo Austral. Ha trabajado en Hawái también, es profesor en la Ludwig Maximilian University de Múnich. Ha estado tiempo allí también como, digamos, profesor asociado. Ha trabajado también en la Universidad de Hawái, donde ha estado 5 años, ¿no? En Hawái, ¿no?
Sí.
5 años en Hawái. Él empezó su carrera en el año 97 y tuvo un PhD, un doctorado en la Universidad de Bonn, y ha trabajado en muchos diferentes campos, sobre todo relacionados con las misiones espaciales. Y ha trabajado también en el diseño, en este telescopio gigantesco que se va a hacer, el European Extremely Large Telescope Project, que es un telescopio gigante que se va a hacer. Bueno, también nos puede contar alguna cosa. La conferencia va a ser en inglés porque se sentía más cómodo haciéndolo en inglés, pero bueno, él entiende también español. Si luego al final queréis hacer preguntas, o bien en español o bien en inglés, y si no, traducir, en fin, que no va a haber ningún problema. Sentiros a gusto y muchísimas gracias, Marcus, por venir, y toda tuya la audiencia. Muchas gracias. Un aplauso para Marcus, por favor.
Gracias. Entonces, buenas tardes. Sí, yo disculpa porque mi castellano no está al nivel que me gustaría, pero bueno, el próximo año voy a repetirlo en español. Entonces, hoy voy a hablar en inglés. So, welcome everybody, and thank you for actually coming and listening a little bit to what we have to say about planets and how to get there. So, if you want to actually escape our planet Earth, I will tell you tonight how to do that. And whether it's worth it. Good, so you heard a little bit about me, and what I'm mostly doing these days is actually taking care of all the space missions of the European Space Agency, all the ones we have in operations for astrophysics, for planetary science, and for heliophysics. But my other job is to be a professor at the University of Munich, where I teach since almost 20 years. And in the last 10 years, I was teaching astrobiology. And so a little bit of what I wanted to tell you tonight is about astrobiology, so what life is. And I divided the talk tonight in 3 parts. I'm going to try to give you an introduction about life, about our universe, which is quite small, not that old, maybe contrary to what you want to think. A little bit what life is there. Then I'm going to tell you what we know about life in our solar system and how to get there. And then in the 3rd part, I'm going to tell you what we know about life beyond the solar system and whether we have a chance to get there. So let's get started. So I think, given the title of the talk, we're going to start looking a little bit at what does habitable mean. So what is life in space? What are we actually really looking for when we say we're going to look for life? So maybe you think that we're going to look for something like that. You know, which is, you know, the question is, are we alone? Is there life elsewhere? So a spoiler, we haven't found life beyond Earth yet, but I'm going to tell you what we're looking for. And the other question we're asking ourselves is, what is life and how did it emerge? Because we know life on Earth, but as long as we know only one form of life, it's difficult to define it. So we are not looking for this. So this is what you might have seen in your backyard or so. If so, many people call us and say, we've seen it. It's like, yes, tell us where you live. And we are more looking for something like this. So these are the simplest form of life, single cells, and that is what we are looking for. And why we're looking for this and what is our chance to find it on other planets or maybe even beyond the solar system, that's what I'm going to tell you about. But let's start with an overview first. And I'd like you to take away a feeling for space and for time. In what kind of universe are we living today? So what happened so far? In fact, you might think of the universe as something gigantic, immense, infinite. It is not. It is not. It's actually quite small. And you might think of the universe of existing forever. You know, it is not. It's actually quite young. Right? So it started about 14 billion years ago. In Spanish, that's 14,000 million years. It's an English billion or US billion. And the universe formed with a big bang. And that's our universe. There might be other universes out there. We don't know. We'll maybe find a way one day to actually know, but at the moment we cannot break the barriers of the universe. But what fascinates me is that with our telescopes today, we can look at the entire universe. So that's wonderful. So I have a quiz for you to start. It's to try to get a feeling how big is the universe really. So I'd like to actually ask you the number of stars in the universe and to get a feeling whether that's a lot or not compared to life, which is the other topic of tonight. We'll look at the number of living organisms in our ocean. So does anybody here know the number of stars in the universe? It's a big number, but not that big. Okay, so I'll give you the answer. So it's 10 to the 22. Okay, so that's a big number. And if we compare that to the number of living organisms in our ocean, and if you don't know the census of marine life, it was a wonderful census which lasted 10 years from 2000 to 2010. You can Google it, and it tried to actually count all the species that we had in the ocean and also to estimate the number of organisms in the ocean. So what do you think? Do you think that it's about the same number of stars as living organisms in the ocean? Or do you think it's less or much less? Or do you think it's more or much more? So we're going to take a quick poll. So hands up for if you think it's about the same number of stars as living organisms in the ocean. No, nobody thinks that? Okay, so who thinks that it's less or much less? Okay, so a few hands up. And who thinks it's more or much more? About, say no, more hands. Okay, so you're right actually, right? So it's 10 to the 30. It's actually a lot more. Okay, so you have a lot more living organisms in our ocean than you have actually stars in the universe. So the universe is not that big. So I like these numbers because first you can count all the stars in the universe, which I think is extraordinary. You know, if you think about it, the universe is not infinite. We know everything which is in it, more or less. And it's not that big because if you just counted the number of living organisms in the ocean, there are 1 billion times more. Good. So the universe is finite, and actually it's rather small. Right? So, but that's the one we live in. So what happened is 14 billion years is the age of the universe, and 4.5 billion years the sun formed, including its planets. So a lot of material came together and actually crushed gravity, just brought all this hydrogen and helium together, and then the hydrogen started to ignite, and then we had our sun, and all the trash around it formed the planets. So shortly after that, the Earth formed. So all the trash around the star, around our star, was this. You had lots of collision, and little by little, you built bigger blocks. And one of the bigger blobs was then were the planets. One of the smaller planets was the planet Earth. And what happened to our planet Earth at the beginning? It was very hot because of all the collisions. So there you had no life. This planet is completely sterile because it's so hot on the surface that you have absolutely zero chance of having any life there. Now, what happened to Earth was very special because Earth actually experienced a major collision in this early time. So this is often called the late heavy bombardment, the first 500 million years. And we were unlucky because we got hit by another object which was almost the size of Mars. And after that collision, which you see here, the Earth was again completely sterilized. So at that point, you had absolutely no chance to have any life on the surface. And that collision led actually to the formation of our moon. So the result of this collision, which happened about 4 billion years ago, led to the formation of the moon. You're going to see it forming there, quite nice. It goes once around, and then ta-da, we have a moon. And the moon, as you know, is formed. It's formed of material from this collision and from material from Earth, which was ejected. And we have that moon today, and we will sooner or later go and colonize it, probably in the next 10 years. So that's where we are after 4 billion years. So if you look on a time scale, this is the Big Bang, 14 billion years ago. And the sun formed and Earth formed 4 billion years ago. So the universe is not that old. It's only 3 times older than our sun, and the sun, or 3 times older than Earth, right? And relatively quickly, actually, after that, as soon as life could form on Earth, life formed on Earth. So that's also something which to me is always surprising, is that if you look on this scale, life exists since almost a third of the age of the universe. Right? And later you formed other things. The Alps, I put the Alps here because I grew up in the Alps, but you can put anything else on there. And then finally the Homo sapiens, which appeared. Right? So you had that gives you a bit of a scale of the time of the universe. So life exists in the universe since at least 1/3 of its age. It means that life is not something which just happened from a small moment and then disappeared again. Life has been here for a long, long time. And maybe life existed elsewhere and has been here since the beginning of the universe. We don't know. Right? But this gives us hope that looking for life is not something completely stupid. Life is not something which just appears in a blink and disappears again and just for a moment. But life is here and there to stay. Okay, so what is life, actually? So I talked a lot about life, and let's look a little bit at what we know. So we use a certain definition of life at the European Space Agency and at NASA, because if you're looking for something, you need to define what it is. Otherwise, everybody could claim that they found life if life is not defined. And our definition is very simple. Life is a self-sustaining chemical system capable of Darwinian evolution. So self-sustaining chemical system means that it's chemistry. It's not something magic. So you and I, we are just chemistry, complex chemistry. We are self-sustaining. We don't need anything else to actually make us, or to actually for us to function. So all we do is we use some form of energy to produce something. Typically, you produce mini-me's. Okay, so you produce copies of yourself. So that's life. Right? But the copies are not allowed to be perfect. So that's Darwinian evolution. So you need to be able to adapt to Earth changing, the universe changing, etc. So the fact that you can adapt and you can evolve is what is meant by Darwinian evolution. So you use energy, you have a recipe inside you, DNA, okay, and you make typically mini-me's, or copies of yourself, but they're imperfect, and some of these copies will be better adapted to your environment than others. So the problem we have with this definition of life is that we know only one form of life. And if you have only one example of something, it's very difficult to define the group because there's only one person in the group. So maybe you think one form of life, but there are many forms of life on Earth. And I'm sorry to disappoint you. No, there's no difference between you, a banana, a mushroom. You're just all the same life. Right? So, and actually, if you look at the cells of a mushroom, they work exactly like your cells. They use exactly the 20 same amino acids to actually go through exactly the same type of DNA to actually build the same proteins as you do. So there's in fact only one single form of life. And the person who had that great insight is Charles Darwin. And I like so much his notebook that I wanted to put it up here. Because what you've probably heard about the tree of life. So that's what he sketched here in his notebook. And I like the top of the page because he just wrote, I think, and then flash, he puts up the best theory of life ever. And so now I will always start my little notebook with I think, but unfortunately I don't have that great ideas. Not everybody liked this idea because when actually Darwin proposed this, the London Times published this picture and said, it's impossible. We are humans, we're much better than everything else on this planet. We cannot possibly be the descendants of apes, for example. In fact, that's what we know today. There's one single form of life from which everything else branched off. On the left in the blue, you have bacteria, so very simple forms of life, single cells. And then to the right, you go off and you have archaea, which are also still very simple forms of life, but then you go to the eukaryotes, and then at the end of the branch somewhere, there's mammals at the very top right, that's us. Right? But it's still one life, same DNA of everybody there, same types of cells, same metabolism. And so there's only one form of life, and it's difficult to define it. So the other thing which is quite important and interesting to see is life very bizarre? And it's not, because it's really based on the most common chemical elements in the universe. So the universe is chemistry, it's full of elements, it's atoms, it's physics. And here you see a periodic table that you probably remember from 6th grade or whenever you actually had the last time chemistry. And what I circled in purple are the 10 most common elements in the universe. So you have hydrogen and helium at the top, the simple elements, and when you go down in this table, the elements become more and more complicated. What I circled in yellow are the elements which life uses. And you see that there's a huge overlap, right? So life is not using some weird elements in the universe. Life simply uses what's most common in the universe. Right? So that's, I think, another good hint that it's worth looking for life elsewhere, because life is not very special to Earth, or it doesn't use very special elements on Earth. Life just uses what's there in the universe. The most common, actually, elements. So life is not weird. Life is actually very simple. And life has been here for a third of the age of the universe at least. So it gives us a lot of hope that it's worth looking for life. So I have another quiz for you. Another of my two favorite numbers is the number of cells forming your body and the number of bacteria in your body. So does anybody of you know how many cells there are in our body? A lot. And we could actually compare that to the number of stars in the universe. But okay, I give you the number. It's 10 to the 13, okay? So it's a big number. So these are our cells. So skin cells, liver cells, blood cells, whatever you want. Whatever forms you. You're just sitting here. And now we also have bacteria inside of us, on top of us. So we'll have the same quiz as before, okay? So do you think we have about the same number of bacteria in or on our bodies as we have cells? Or do you think we have less or much less bacteria? Or do you think we have more or much more bacteria? So, okay, so who thinks it's about the same amount? Nobody thinks it's the same amount. So who thinks it's less or much less? It's only one person, 2, 3. Okay. So who thinks it's more or much more? I assume everybody else. Okay, so you're still counting. So in fact, we have about 10 times more bacteria on our cells. Now, so what does it mean? Because, okay, you guessed maybe that right. But it means that when I stand here, or you sit there, most of the living cells are not yours, right? They belong to other organisms. So you think you came with your friend or boyfriend or partner, but in fact, next to you, there's 100,000 billion organisms sitting there just next to you. Right? So now you're completely confused. You say, but which one is my boyfriend? The big one. Okay. But the other question is, okay, why do we still look? Why do you still look like a human if most of the cells that you see here are actually not mine? It's me, yeah. I mean, it's me plus my 100,000 million billion friends. But so how can that be? So I'm going to show you the answer there in the next movie, but it's full of blood, the next movie. So I don't know if you're under 18, you must love blood, okay? So here it is. So that's blood, okay? So that's, all of this is blood. The round cells are actually red blood cells. The big cell in the middle is actually a white blood cell. And the little point, black point on the left of the white blood cell, that's a bacteria, right? And that's the answer. So you have different types of cells, and actually bacteria are prokaryotes. So these are cells without a nucleus. They're very tiny cells. They're life in the simplest form. And if you are a mammal like us, you're actually a eukaryote. So your cells have a nucleus, and they're 10 times larger. actually 10 times in one dimension. So in volume, it's 10s, times 10s, times 10. So it's 1,000 times larger. So the cells of your body are 1,000 times larger than the cells of a bacteria. And that's the answer. That's why you can have so many other cells inside you, but you still look like a human, because you have less cells than the other guys, but your cells are bigger, okay, 1,000 times bigger. But I wanted to show you here, because this is your blood, and this is what's happening in your blood right now, okay? So here's a movie. It's with an electron microscope. So A, the bacteria is trying to escape. I hope you noticed that. But B, your blood is actually quite efficient. And the role of the white blood cell is to destroy the bacteria. But this is a single cell, okay? And this is what's happening inside you right now, okay? Or of all of us. Or you probably all have caught some bacteria somewhere, and your cells are destroying it. But what it means is that you're standing there, and maybe you're sitting and watching, etc. But a lot of things are happening inside you, and things at even a single cell level, which can actually detect, chase, destroy other things, right? It tells you a lot about how life, even simple life at the beginning of the formation of life, could actually execute complex tasks. So what about life? To just wrap this up, and then I'll talk about how we actually search for it. Life started at least 3.7 billion years ago. So almost as soon as the Earth was not sterile, as soon as the Earth cooled down again, we could actually start developing life, and life formed almost immediately, which is another good hint that life is not so difficult to produce. Life formed almost immediately when it could on Earth. Okay? So that gives us hope that maybe on other planets it was the same. Life happened maybe immediately when it could. So 3.5 billion years ago, life had the good idea of using the energy of the sun as opposed to thermal energy or chemical energy. And so it started to do photosynthesis. And then a little bit later, from these very simple cells of bacteria, it went to more complex cells, which are the eukaryote cells. That happened about 2 billion years ago. And then these were still single cells. About 1.5 billion years ago, we started to have multicellular life. Multicellular life, so organisms which had many, many cells, but all of these cells were the same. So we had organisms where every cell did had the same function, but together they were actually stronger than single cells. And only about 500 million years ago, which is quite recent, even if the number is big, we had actually specialization of cells. So what you and I are, we started, each of us with a single cell, and this cell divided into 2, into 4, into 8, into 16, into 32. But every one of these cells was not the same and does not have the same function as the previous ones. These cells managed to specialize. So you are made of many cells, but you have actually skin cells, liver cells, blood cells, etc. So this is when life invented how to specialize cells in one single organisms, the diversity of life completely exploded. And that's what this Cambrian explosion is. 500 million years ago, we started to have all kind of vegetation, life, animals, insects, etc., etc. And then eventually dinosaurs arrived 200 million years ago, and Homo sapiens again. So we are here just today. Right? During that time, life actually did something very strange to our planet. Because our planet started with an atmosphere of CO2, and that was about it. But when life invented photosynthesis, one of the trash products, so one of the debris of photosynthesis, is actually oxygen. So it started to actually put oxygen in the atmosphere. And oxygen, in the course of time, grew. And only when there was enough oxygen in the atmosphere, like today, with 23% or so, oxygen is very efficient, and other organisms, like us, learned to breathe the trash product of photosynthesis. So what we are doing, what you are doing, what I'm doing, is actually breathing the trash of photosynthesis. Yeah. But it's so efficient that you can actually form big life forms. Dinosaurs, humans, we're big, okay, as opposed to things which don't use oxygen. Good. So one thing to remember is, on Earth, life changes the atmosphere. And at a big scale, it changes the entire atmosphere. So our complete atmosphere changed many, many times during the course of the history. So then, I don't want to talk about it today, it's another talk, but I make a small parenthesis. You say like, oh, but so the climate change, yes, we are doing climate change, and that's what life has always done since 4 billion years, we're changing the climate. Right? And when I say that at the university, the students say like, oh, so it's all good. So it's like, yes, it's all fantastic. The next lecture will be mass extinction. And every time we had a climate change, we had also a mass extinction. So be sure that this time we're changing the climate. We're not the first ones to do it. It has happened all the time before. And every time, it never failed. We had mass extinction following it. And mass extinctions usually starts with the biggest organisms. Right? They're the most complex. They're the ones who are the most fragile. They go first. Okay, dinosaurs go first. Right? So now you can actually look at who are the biggest ones on this planet. And I'll let you think about that for tonight. Okay, mammals would be a good tip. You can think of, if you belong to the mammals, avoid mass extinction. It's going to hit us. So we'd better take care and try to actually avoid climate change, because climate change means mass extinction. Good, but I didn't want to actually talk about this tonight. So, second part of the talk. Let's see whether we can find life beyond Earth. Right. And let's start simple. So let's start in the solar system. But we're going to use two things, okay? So what we know about life. One is that life changes the atmosphere, and also about life itself, which is that life, as we know it, the cells, all of your cells, to do the chemistry inside the cell, you need water. Water is a solvent. You need water just to actually have all the other elements inside there and to combine and to connect and disconnect and to do chemistry. So this is the planet Earth. And if you strip it from the atmosphere, then you're left with a lot of ocean. And it looks very blue. Right? So we always think of our planet as a blue planet and lots of water. But in fact, if you took the water on the surface and put it into one ball, that's all there is. So there's actually not that much water on the surface of Earth, which, by the way, means that you should not put your trash into the ocean. The oceans are not that much water. But all of that water is used for life. And we're going to actually now look for life in the rest of the solar system. So here we are, that's the solar system. The sizes of the planet here are to scale, but the distance between the planets is not. Okay, the distance are much, much further apart. But you see a little bit what the size of the sun is on the left compared to the size of Earth. Earth is actually quite small. All the inner planets, the telluric planets, are quite small. And then the outer planets, the gas planets, are quite big. So let's start with Earth. We know that there's water. Let's go and look next to us, so on Mars. So what do we know about Mars? We know a lot about Mars. So here you see all the missions we have sent to Mars since the 1960s. At the top, we started in the 1960s, and if you go clockwise, you see all the missions, everything we have sent to Mars. And we actually visited Mars something like 60 times, which is more often than we visited the Mariana Trench, so the deepest place in the ocean. So we know Mars better than we know the deepest point of our ocean. It's a bit embarrassing for our ocean, but it also tells you how often we actually went to Mars. And we have now rovers on Mars and helicopters and all kinds of things. So we know Mars quite well. We have studied it for a long time. In particular, oops, sorry, this jumped one slide, 2 slides. Sorry, I'm going back. You're going to see this again. Sorry, here. In 2003, I wanted to show you just 2003. That's about 20 years ago, because we just, this was one mission of the European Space Agency. So it's a mission which is still orbiting Mars. So it's one of the missions that is under my department here in Madrid. So 2003, and it just celebrated its 20th anniversary. And this is the image of the 20th anniversary of Mars. And you see on Mars that we orbited it now since 20 years. Mars is a little bit further than Earth. So Mars takes 2 years to go around the sun, not just 1 year like the Earth. And in 2 years, so we actually observed Mars for 10 Mars years. So we know its climate, we know winter-summer differences, we know where there's water underground, we know what the atmosphere looks like, we know the temperature changes. Like on Earth, the temperature is higher at the equator than at the pole, etc., etc. And this picture that you see there, the colors indicate the geology, so the minerals that is there. And you can zoom in this image, and we have this image that the real resolution of that image is 50 meters. Right? So you can detect this planetarium. If there's a planetarium on Mars, we actually have it on our picture. We looked, there's no planetarium on Mars. Right? So, but you see that there's actually a canyon, which is much larger than the Grand Canyon. On the top left, Olympic Mons is one of the, or it is the largest volcano in the solar system. We know that the entire northern side is actually a little bit lower, and all this northern side used to have an ocean, but the ocean evaporated. What we are doing next, and this is actually, it's an animation. This rover is actually not, actually this rover, there's a rover on Mars which is currently drilling, putting samples in tubes. And the next missions we are planning is to actually go get the tubes and bring them back to Earth. So the tubes are being readied now. And the next missions that we are preparing will bring back these tubes of material from Mars in about 10 years or so. So we will have material from Mars that we can study and look again for life. But what we know until now is that there is water on Mars. It's underground, but there's a lot. Right? Mars used to have an ocean, but it evaporated because Mars is much smaller than Earth, and so it could not retain the atmosphere. The atmosphere of Mars is very, very thin, and that means also that the water evaporates very quickly. So the ocean is gone, but there could have been life because, as I told you, on Earth, life formed immediately. So on Mars, maybe also life formed immediately. It just probably left when the ocean left. There's a very thin atmosphere on Mars, but it's only CO2, so it's not useful to actually search for life. So we have not found life on Mars, but we will keep searching. So it's a place which is not that far away. You can go there in a few months. And so we will actually keep searching for Mars. And it's technically, we could already colonize Mars. It's just expensive, and it's typically a one-way ticket. And at the moment, we don't sell one-way tickets to Mars. We prefer to have return tickets. But this is going to happen maybe in my lifetime, certainly in the lifetime of the youngest people. So that's one place where we look for life. The other place where we look for life is all the outer solar system. These are gas planets. So on the top of the planet, you will not have life, probably. It's not liquid water. But most of these planets have actually moons. And here's a collection of some of these moons. You see Ganymede, which is a moon of Jupiter, Titan, which is a moon of Saturn, Mercury, which is actually smaller. So one of our planets is smaller than the biggest moons in the solar system. Then you see Callisto, which is another moon of Jupiter, Io, which is another moon of Jupiter, and our moon. Our moon is actually pretty big. Right? Europa, which is another moon of Jupiter, and then Triton. Pluto, you see Pluto, it's a planet, but it's so small that we dismissed it. A few years ago, we decided, look, it's not worth calling it a planet. Right? But these four are moons of Jupiter, and you see that they are some of the largest objects in the solar system. And if you followed the news, if you read the newspaper, you looked TV, etc., 2 months ago, you probably saw that we launched a mission to actually explore exactly these moons. It's called the JUICE mission. It's not the first mission we're sending to Jupiter, but it's the one which is going to actually study these 4 moons to see whether they are habitable. Because what we know of these moons, they're far out, they're far from the sun, so the crust is ice, so it's so cold that it's all ice. But below the ice, we know that at least for Europa and for Ganymede, there's water. There are oceans below the ice. For Callisto, maybe as well. Io is volcanic. It's too close to Jupiter. But in fact, if we look at Jupiter, then this is the mission that we are sending there. We have launched it on the 14th of April, so it's on its way now. It takes a while to get to Jupiter. It's longer than from Madrid to Barcelona. It's about 7 years. So if you take the very slow train, I think Renfe can take you in 7 years to Barcelona. But 7 years to actually wait, and then we're going to be there, and we're going to be able to study the moons of Jupiter. Jupiter has actually something like 80 known moons, maybe even more. But the biggest one, Io, Europa, Ganymede, and Callisto, these are the ones we would like to actually go and see. And why? Because if you actually compare the amount of water in Europa compared to Earth, I showed you this image before, Earth on the left, and the amount of water we have on Earth, Europa has actually more water than Earth below the surface. So if life needs water and life forms immediately in water, then Europa is actually a quite good place to actually search for life. And that's why we're flying there. And this is, because I thought if you come to an observatory, this is the launch. So this is 2 months ago when we launched the satellite. So we're just going to see a rocket launching because it's fancy and it's nice. And we love to actually send rockets into space. But that is departure for Jupiter. And I speak French because our space center is in Kourou, in French Guiana, so north of Brazil. And there we go, off to Jupiter. So I'll come back in 7 or 8 years and I'll tell you whether we found life in, over there. We're not going to watch the movie for 7 years. I'm going to skip. Okay. What about Saturn then? So Saturn is also one of the giant planets. Saturn also has many, many moons. More than 60 moons are known, 70 or so at the moment. Stop counting. And it has some pretty big moons as well. You saw that the second biggest after Ganymede is Titan. Titan is the moon that you see here. You see Saturn on the right. You see the rings of Saturn from edge on. And you see the big moon. It's actually Titan. You also see another little moon on the right, if you look very carefully, just below the ring on the right there. That's Enceladus. Enceladus, like Europa, has a lot. It has an ocean below the crust. So also there's water below the crust of ice. And we actually see geysers coming out. So there's cracks in the ice, and there's water coming out. And so one of the ideas is to fly there, to collect the water, and to look whether we find anything organic inside the water. But I wanted to talk about Titan, because Titan is maybe even more interesting. We did fly to Titan. The Cassini mission, the NASA Cassini mission did fly to Titan. So it was launched in 1997. And at the end, it observed for 20 years Saturn and fell into Saturn and ended its life. But it had a passenger on board. The passenger was from the European Space Agency. It was called the Huygens probe. And the passenger is what you see here as a picture. The passenger was a probe which you could actually drop and which would land on Titan. Because Titan has an interesting property. It has an atmosphere. So with Venus and Earth, Titan is the only third and only other object in the solar system which has a thick atmosphere. A thick atmosphere means you can use parachutes. On Mars, parachutes don't work that well because the atmosphere is very thin. But on Titan, they work well. And so we used just a simple parachute and dropped the probe, and actually it landed and survived a few minutes on the surface of Titan. What we saw there is that there are actually lakes on Titan. But these are not water lakes, because you're so far out in the solar system, the temperatures are so cold that water would be frozen. So these are methane and ethane lakes. And ethane and methane are liquid at these temperatures. So if you have life there, and this is what we would like to actually discover, then life would not be like the one instance we know here. It would not be life based on water. It would be life based on a different solvent. It would be maybe life based on ethane or methane. Right? So that's another place we would like to look for life. And we're actually slowly planning on how to best go there. We know we can go there. We know we can land there. We have done that before. And now we need to actually transport the material there to actually look for life. So if we take a summary of our solar system, we looked on Earth and we found life. Then I'll give you another talk about intelligent life, okay? But that's a different story. It's actually interesting to actually understand whether we could find intelligent life elsewhere. Mars actually quite likely had life if life formed very instantly, but we haven't found it yet, but it's a very interesting place to look. The moons of Jupiter are a very interesting place to look. The moons of Saturn are a very interesting place to look. And in fact, I didn't talk about Venus, but Venus is the other one which has an atmosphere. It's close to the sun, it's very hot, but you could maybe imagine life forms there as well. So there are lots of places in the solar system which could host life, and that's why we actually continue and continue and continue to actually search for it. And as I showed you, we can actually fly out in the solar system. There we can actually get there, and we can bring material there, and we can bring instruments to actually search for life. And at the moment, we live in a super exciting time because the space sector is currently completely exploding. There are so many space agencies, the European Space Agency, NASA, the Japanese Space Agency, JAXA, the Chinese, CNSA, Roscosmos from Russia, ESRO from India. Even the UAE has now a satellite orbiting Mars. So a lot of these space agencies are currently going and looking at our solar system, at Mars, at Mercury, at Venus, at Jupiter. A lot of time we actually just have commercial interests, so actually we want to actually maybe mine and do other things, but all of them will actually give us opportunity to maybe find life there. So very exciting. If you're young, join the space agency. Okay? If you're old, join the space agency as well. Good. But so let's then talk about the last part, the last third, life beyond the solar system. So do we have a chance to actually find life beyond the solar system? Let's have a look. Okay. So I told you that life is transforming the atmosphere of planets, and that's the chance we have. Right? So what happened in the last 20 or 30 years? We look up, and instead of just having the sun with its planet, we have now 10 to the 22 possibilities. Right? So this is actually a picture when I used to live in Hawaii. You know, that's the night sky we had in the backyard. So I think 1% of the human population can see the Milky Way from its backyard, and I was happy that my kids could. What we learned is every star you see, so when you go out tonight of the planetarium, look up, and every star you will see on this on the sky is likely to host a planet. So we know that we have 8 planets in the solar system, and when I looked earlier this week, we have 5,370 planets known beyond it. Right? So that's already the number of planets we discovered beyond the solar system, around other stars. Statistically, what that means, right, because you can do that using statistics, is that really almost every star in the sky hosts a planetary system. So we have 10 to the 22 planetary systems probably in the universe. Right? So that's a lot of places to look for life. Now the question is, which of these planets is habitable? And the way we think about it is, I'll just explain that for a second. Where can there be water? So the blue band here is water in the center. And what you have at the bottom is the distance you are from your star. Okay? So if you're on the left, you're very close to your star. If you're on the right, you're very far from your star. So if you're on the left, it's very hot because you're very close to your star. If you're on the right, you're very far from your star. It's very cold. Now, the stars are not all the same. So at the top there, you have the sun. And then if you go down the scale, you have smaller and smaller stars. You can also have bigger stars than the sun, but they are quite short-lived and they're quite active. And so for life, it's more difficult. So we tend to look at stars which are the size of the sun or smaller than the sun. So if you're the size of the sun at the top, you see the planets, Mercury, Venus, and you see that actually the blue band crosses Earth, crosses Mars. So Earth and Mars could have water on the surface, and they did, so we know that's correct. And then you have Jupiter, Saturn, Uranus, Neptune. That's too cold to have water on the surface. But we know about the moons. Now, if you go down, you see actually the band, and we have now many, many planets which lie in this blue band. So how do we actually learn about these planets? How can we characterize these planets? Okay, so how can we actually get their properties? And then the last 20 years, and there was a Nobel Prize for this in 2019, we developed 2 techniques. This is one technique on how to discover whether there's a planet around a star. And the star is at the center. It's not to scale. Huh? The star would be much, much bigger, and the planet would be much, much smaller. But we cannot see the planet. The planet is dark. It doesn't shine itself. We can only see the star. With our telescopes, on the ground or in space, we look at the star. And if there's no planet around the star is just still. But if there's a planet around the star starts to actually wobble, because the star feels the gravity of the planet. The planet is, of course, very light, so it's still the planet turning around the star, not the star turning around the planet. But the star wobbles enough that if what we can see with our telescopes is a spectrum at the bottom there, and we will see the spectrum move. And if the spectrum moves, it tells us, there's a planet around the star. If the spectrum doesn't move, we know that there's no planet. But we can learn much more, because if you look at the spectrum moving, if the spectrum moves, for example, with a 1-year cycle, 6 months to the left, 6 months to the right, 6 months to the left, 6 months to the right. This could be a planet Earth, because Earth goes around the sun in 1 year. If it takes 10 years, if it takes 5 years to the right, 5 years to the left, 5 years to the right, 5 years to the left, then it could be a Jupiter, because Jupiter takes 10 years to go around the sun. Right? So 10 years means that you need a lot of measurements. You need to be very patient. But there are also some way which move in days. Then we know that actually there's a planet there, which is very, very close to the sun. And this is how we actually can learn about the period of the planet. And also by the size of the movement, we also learn about the mass of the planet. So with this technique, you can learn about the mass of the planet and where the planet is. So that tells you already one thing. Then we have another technique, a second technique. If you're lucky, the planetary system is inclined in a way that the planet will pass exactly between you and the star. And then you have, like here, a shadow exactly on top of the star. And there are enough cases like this, because we have 10 to the 22 to select from. There are enough cases like this now that we have hundreds and thousands actually of these cases. So what can you learn if you do this? You can actually measure the size of the shadow, right? Because the star is bright. This is a curve that you see at the bottom. When the shadow passes in front, the star will be not quite as bright. So you will be at the bottom there, the curve. And then when the star is going to go away, when the planet is going to go away, the star is going to be bright again. So you can measure the size of the planet. So from the technique before, you can measure the mass. From this technique, you can measure the size. And if you have the mass and the size, you can divide the two, and it gives you the density. And if you have the density, you know whether it's a very heavy planet made out of iron, or whether it's a very light planet made out of gas, or if it's a planet in between made out of water. And so we have these techniques, and for hundreds of stars now, we can actually determine what type of density they are. There's one more advantage if you do this, is that when this happens, there's light from the star from behind, which is going to shine through the atmosphere of the planet, and is going to reach you. And if you make a measurement now with the light through the atmosphere, and you make another measurement when the planet is gone, you can compare the two. And this is going to tell you what the atmosphere of the planet is made of. So you have kind of a backlight which illuminates the atmosphere of the planet. And you can measure the composition of the atmosphere of the planet. And then you see something like this. Okay? And I told you, life is changing the atmosphere of the planet. So if we can measure the composition of the atmosphere of the planet, we can actually go and start searching for life. On the left, you have visible light. On the right, you have infrared light. And I gave you 3 examples. Right? Venus is at the top, Mars is at the bottom, and the Earth is in the middle. So if we look at Venus, we will see a very thick atmosphere. But that atmosphere is also almost just CO2. And so what you see when you actually take a spectrum of the atmosphere of Venus is just CO2 lines in the spectrum. When you do the same for Mars, Mars has a very thin atmosphere. So in the visible, you see almost no deep lines, but it's the same lines as for Venus. It's also almost just all CO2, just weaker. And it's only when you look at the atmosphere of the Earth and you compare that you actually see an atmosphere like this. When you start to see water, H2O, you start to see oxygen, O2, ozone, O3 on the right, methane. And with these elements in the atmosphere, you can actually start deduce whether there's life or not. Because, for example, oxygen is not a product which actually can easily be generated geologically. Oxygen has to be generated in these quantities and stable together with methane, CH4. It has to actually come from life. So it's only because there's so much life producing oxygen trash on this planet that we actually can see these lines. So if we were to look at Earth from very, very far away, we would actually be pretty sure that life exists on Earth just by looking at this spectrum. And that's what we're trying to do for planets beyond the solar system. So we don't have quite yet the sensitivity to actually detect this, but we're actually working on it now with our telescopes. So we have lots of telescopes that we are preparing. In the middle, you see the James Webb Telescope. We launched that together with NASA 2 years ago. At the bottom right, you see the Hubble Space Telescope. It's just celebrated its 33 years. Then on the top right, you see Ariel. On the top left, Plato, which are 2 missions which we're going to launch in 2027 and 2029, so in 5 years from now. At the bottom left, you see Cheops. So this is another satellite which is flying at the moment, which we launched 3 years ago. So there's a lot of space missions at the moment trying to just do this, characterize exoplanets, and with a bit of luck, detect life in the atmospheres of these exoplanets. And we're not only doing that from space, we're also doing that from the ground. And on the ground, we are actually currently building the telescope there on the left. So that's the European Extremely Large Telescope. That's the largest telescopes humankind ever built. is being built right now in Chile. It's going to be finished in 3 years, 4 years from now. And you see, compared to the pyramids, that it starts to be a massive telescope. Just the mirror is 40 meters diameter. So probably twice, what's this size here? Probably twice the size of the diameter of the dome. So half a football field. Half a football field of a mirror, which is polished to better than actually tens of nanometers. So if you take your hair and you drop it on that mirror, that will be the biggest bump on that mirror. Right? So half a football field, which is much smoother than even the thickness of your hair. And with that, we can actually start to do the measurements that we need to do to actually find life. So humankind is producing a lot of technologies for this. So if life exists beyond the solar system, within, my guess is the next 2 decades, we will actually detect it. So I think in most of our lifetimes, I wish you all to live another 20 years, and then you will maybe, if life exists nearby, have discover life. So what I wanted to finish with is to just let you know whether we have a chance to actually get there. So within the solar system, you saw that we are pretty good. We can fly almost everywhere. Lots of space agencies trying that. Now, what about beyond the solar system? So let's just finish for fun on this. So first of all, what happened so far? How far did we get? So this is a little bit of the history of our conquest of the of space. About 50 years ago, 60, 70 years ago now almost. We had Sputnik. That's the first time we launched something in a man-made objects beyond Earth and just in orbit of Earth. 50 years ago, or 54 years ago now, we landed on the moon, and we're going to soon repeat that. And then the first time we landed actually on Mars was in the 70s. So in the 70s already, Viking 1 and Viking 2, the 2 missions of NASA, landed on Mars. The pictures you see there is actually just the engineering model of one of the Viking probes, and next to it you have Carl Sagan, which is was a famous scientist and also a science fiction writer. But you see that actually we've been flying into space since quite some time. Now the problem is we are trying to actually get to the next stars, to Alpha Centauri, and that's the distance. So on the left you have the Sun. Then at 1 astronomical unit you have Earth, at 10 astronomical units you have Saturn, and then at 100 astronomical units, 10 to the 2, you start to actually have the heliopause. So that's when more or less the influence of the Sun stops, and then you need to go 10 times further, and 100 times further, and 1,000 times further, and 10,000 times further until you reach the next star. So you are here, right? So that's where we start from. So let's look at how far humans traveled. So far, humans traveled, well, to the moon. Okay? So it's not much further. But how far did we actually go and land? I showed you that we landed on Titan. So this is also how far we actually got with a man-made landing. And if you look at the furthest we went with a human-made object, we have the Voyager probe, which actually passed Pluto a few years ago and is actually on its way out. But that's how far we got. Right? And this is a logarithmic scale, so you see that it's always 10 times further at every step. So we are not getting even close to the next star. So how do we get there? So the distance here is in astronomical units. If I were to give you the distance in light years, it would be about 4 light years. So 4 light years means that you need 4 years if you were to travel with the speed of light, which is as fast as anything moves according to the laws of physics that we know today. Right? So 4 years if you can move with the speed of light, but then all kind of relativistic effects kick in and you're completely torn apart, etc., etc. On Earth, we can accelerate things to almost the speed of light. Of course, light travels with the speed of light, but we also have particle accelerators where we get to 90% of the speed of light. But safe, without destroying your electronics, you maybe can go to something like 20% of the speed of light, which is already a hell lot of a speed. Right? So can you do that? And is it worth doing it? So here you have another view, the Sun in the center. The closest star is actually Proxima Centauri and Alpha Centauri. And we know now, we have actually done an experiment called the pale red dot, that indeed these stars host planets, and indeed these planets are in the habitable zone. So it might be fun going there. So it's worth trying. Okay, so it's not useless to try to get there. but you have to actually accelerate to 20% of the speed of light. So accelerating a human to 20% of the speed of light takes a lot of energy. And that's almost impossible to do it today. But there was another concept called a Starship concept, which was actually sponsored by the Breakthrough Prize Foundation, which is one of these foundations in the US. The people who actually are behind this foundation are people like Zuckerberg, Sergey Brin, and these type of people. Actually, I was lucky enough to be in one of the in the concept team, and the concept is the following: you actually need a lot of energy, but not an impossible amount of energy, and you need a very light spacecraft. So this, what you see here, is 4 grams. Okay, there's a chip in the middle. That's a spacecraft. There's a star chip. It's 1 gram, and the solar sail, which is about 2 by 2 meters around it, is about another 3 grams. Right? And then you need a gigawatt about of laser, which is possible. It's really all pushing the technologies, right? But it's not completely out of reach. So it's still a little bit of science fiction, but we're soon there. And if you manage to actually put your gigawatt of energy onto the solar sail, you can accelerate in 3 minutes. You can accelerate that 4 grams to 20% of the speed of light. And if you travel with 20% of the speed of light, it's a fifth of the light speed. So you need 20 years to get to Proxima Centauri. And the idea there is that you would put actually a spacecraft into orbit. You would put 1,000 of these little space chips in. And every day you would actually free one and push one in 3 minutes and accelerate it to the 20% of the speed of light and send it on its way. And the next day you do it again. And for 3 years you do 1 per day. And then you have sent 1,000 of these spaceships towards Proxima Centauri. You cannot brake, so you're going to pass Proxima Centauri with 20% of the speed of light. So you have kind of a very short time to make a few pictures. My proposal was to actually put bacteria on top of the spaceships. We know that there are some bacteria which resist interstellar travel, and we just then colonize with bacteria. So some people think it's a good idea, others think that it's maybe not that good of an idea. But it's a fun way to get there. So it is actually technically we're at the edge of the technology of being able to send something to the next star. It's going to take 20 years, even at 20% of the speed of light. It's not going to be humans. It can be just chips. And if you want to, you can send bacteria on its way. You can hope that it survives. You need to hope that it survives the interstellar travel. But it's actually to actually give you a feeling that it's not possible, but it's not completely impossible yet. And most of what our jobs are as scientists is to actually turn the impossible into something possible. And we did that for many centuries. So I wanted to finish here. I wanted to actually leave you with a few ideas. So first, I think within a few decades, a couple of decades is my guess, we will find life beyond Earth, if it exists. So if indeed it's so easy, life, I showed you, is simple. It uses the 10 most abundant elements in the universe. It has been there for at least a third of the age of the universe. It appeared on Earth immediately as soon as it could. So all of that gives us a lot of hope that it's not something very special, but it probably happened elsewhere as well. And in that case, we are very close to actually getting to discover it. I also think that in the next 2 or 3 decades, we will start colonizing the moon. That's going to happen actually this decade, and probably Mars soon after. And then we're going to start sending probes, as I just told you, probably even beyond the solar system. And unfortunately, within the known laws of physics, human will not soon travel outside the solar system. So be careful with this planet, because there is no planet B at the moment for humans. And beyond that, I think there's a lot of hope. And I wanted to finish with one short movie, which is going to take you from the Big Bang to the humans. So it's going to summarize in 1 minute what I told you in about 1 hour. And that's this movie. That's the Big Bang. And the formation of stars and galaxies. And 4 billion years ago, the formation of the sun and the planets, of the moon, and as soon as it could, life developed on Earth. First as single cells, then as multi-cells, and then as complex organisms. And that is now the very recent history. Mass extinction. Invention of the telescopes 400 years ago. First space flight 50 years ago. Oops. Thank you very much.
Muchas gracias, Marcus, por tu fantástica y maravillosa charla. Ha sido, ¿verdad?, una de las más importantes y más bonitas y más bien estructuradas, ¿verdad? Te lo digo en serio.
De nada.
Y bueno, pues nada. Si queréis hacer alguna pregunta, nos levantéis la mano y Marcus, o bien en español o en inglés, como queráis.
Pues probablemente contestaré en
alemán.
En alemán o francés, no mis idiomas preferidos.
Pregunto en español. Muchas gracias por la charla. ¿Cuál es el límite de exploración de elementos en atmósferas extrasolares? Me refiero, ha mostrado CO2, water, CO2. ¿Es posible to examine amino acids or hydrocarbons or perhaps lipids? Is possible in your condition of astrobiology?
So the what we can detect in atmospheres, so beyond the solar system, needs to be in gas form, because it needs to actually be in the atmosphere, and it needs to be very abundant in the atmosphere. So there we are limited to gas, so to the molecules, the most common ones, as you said, oxygen. Well, oxygen if there's life, but typically CO2, nitrogen. Nitrogen is difficult to detect. Methane is common, but methane is also volcanic, so it's not proof for life. So beyond the solar system, it's only gas. But inside the solar system, we're actually looking at a lot also at meteorites, at comets, and so on. And you mentioned amino acids, because that is actually something which really are the basic building blocks of life. And we see amino acids everywhere where we look. So every time we analyze comets, meteorites, etc., we see lots of amino acids. There are hundreds of them. Now, life as we know it only uses 20 or 22 of them to form the proteins. But amino acids in a planetary system like ours are very abundant. So we know that actually not only the very simplest elements for life are present in the solar system, but also the more complex building blocks that you need, like amino acids.
I saw there is a huge contrast between the massive satellite the ESA is building, you showed right next to the Giza pyramids, and the Starship concept. So what is the reasoning behind building such a massive and costly satellite when you could just make cheaper ones through just shooting laser beams?
So the comparison with the pyramids, this was a ground-based telescope, right? We're not trying to send that into space. It's far too heavy. It's thousands of tons. What we scientists want to do every time we explore the solar system is to bring as much material, as much experiments as we can to the other planet. So the only limit for us are the engineers. Okay. So the Starship concept, if you want to fly very far at very high speed, it's just because you need to accelerate it to the speed of light, that accelerating a heavier mass than a few grams would require so much energy that that's even, I mean, it's even more difficult to generate than the gigawatts that I showed you for just accelerating 4 grams. So very light if you want to travel outside the solar system. If you want to travel inside the solar system, then what we like is to send as big telescopes, as complex telescopes with as many cameras and instruments on board as we can. And that's when we build the largest possible satellites that the engineers allow us to build, and we try to put them on the largest rockets that actually the engineers will give us. So in that sense, the more we can pack into a satellite, the happier we are. And inside the solar system, you don't need to travel. I mean, you can travel at normal speeds. Normal speeds is like 50,000 kilometers per hour. Okay? That's our cruise speed to Jupiter, for example. And that we can go with a few tons. And a few tons means that once you arrive at Jupiter, or once you arrive at Saturn, you can still actually have build a lander which will survive the lander. You need a large enough parachute. You need something which actually absorbs the shock, and then you need the instruments to survive. You need batteries on board. You need telecommunication systems. So all of that, it gets better and better. We get to actually miniaturize satellites, and a lot of satellites, commercial satellites nowadays, are actually nano satellites or cube satellites, so 10 by 10 centimeters. So these in Earth orbit can do a lot of things, and you need to send up a lot. But when you travel all the way to Jupiter, that is, you're not going to send 100 spacecrafts because they're expensive. So the JUICE spacecraft I showed you costs 1 billion euros, right? So 1,000 million euros, which means that we took 2 euros from you, from each of you, actually, from each citizen in Europe. We took 2 euros and we built a spacecraft. So it's, you know, it's not an enormous sum, but it's still expensive. So you're not going to send 100. And so if you go only once every 10 or 20 or 30 years to Jupiter, you build the largest spacecraft you can, and you put all your ideas into that spacecraft. That means, you know, typically 4 tons, 5 tons, 6 tons, the maximum that one of these rockets can accelerate to 40,000 kilometers an hour to escape Earth, and then we go. So that determines a little bit the size, but it's very variable. And in the past, everything needed to be big in space, and now more and more we're actually miniaturizing. And especially for everything which is commercial, because it's also cheap, because it's easier to launch, we build the smaller things. Starlink, which is the network of a few thousand satellites, it's one of the companies doing this type of networks around Earth. There are satellites which are that size, right? And they're launched 30 by 30. So yeah. That's a totally different talk. I'll come back and talk about spacecrafts if you want. In the meantime, you can play Kerbal.
Thank you for your presentation, and congratulations for your work. I wanted to ask something related to something you said towards the end, which is when you send an object, an aircraft, to a planet or one of those moons, and assuming that it is impossible to 100% sterilize the objects that we send there, could it happen that or how do you avoid that bacteria or microorganisms from us, from the Earth, go to those planets? How do you avoid that? And could it be at the end that we, you know, transport our own life to those planets, and that life ends up, you know, evolving and creating organisms there? Do we want that, or if not, how can we avoid that? Thank you.
So there are multiple answers to your question. Let's start with outside the solar system. When we go outside the solar system, there's no law. So you can do whatever you want, Wild West. Okay, so we can send bacteria outside the solar system. Inside the solar system, there's international space law, and they have also something which is called the Planetary Protection Act. So in principle, all the space agencies, when we send something to some other planet, we should sterilize it well enough. And we typically do that, although it's not simple, but we typically try to do that. In many cases, the conditions on this other planet are so harsh that even if you don't sterilize perfectly your spacecraft, either at the re-entry, or not the re-entry, the entry into the atmosphere, etc., you will probably sterilize it anyway. So that is the simple question. Now, there used to be also protocols when you bring something back, coming from the moon back, etc., to re-sterilize everything there. But it's very expensive, and actually, frankly, the space agencies start to save money in sterilizing, both on the way out and the way in. So we could actually transport life between different planets. Now, the other question is it bad or is it good? Right? So, in fact, we know we can find debris of Mars on Earth, and the opposite, we can find debris of Earth on Mars. So we know that there was exchange of material between these two planets, for example. And there are theories which say that life was maybe developed on Mars and came to Earth, you know, during this early phase of the solar system, and maybe the other way around. So we probably, even without human intervention, already polluted each other inside the solar system. So I don't think it's as dramatic as we think it is. And then if you're in my radical camp, then I want to actually bring life out to where there's no life, okay, to just give it another chance to survive longer than on Earth, although it's going to survive forever on Earth, I'm sure. Humans, maybe not, but life, easily.
Hi, thank you so much for everything. I would like to ask like 3 questions. So the first one is, do you think we will be able to travel to other planets for holidays or just visiting it? And how many years would that take to reach that level? The second one will be, I don't know if you will remember, but I will still tell it. Will we humans be able to reach the speed of light in the future? And the third one is, what will happen if you find life on another planet?
Okay, so I'll start with the first one. Okay, so will we be able to do space tourism? I think we live in a capitalist world, so if you pay enough money, you'll be able to do everything. In fact, you can already buy your holidays on the International Space Station, right? So there's space agencies which will take you there. Axiom, if you want an address, I can give you, and if you have enough money, I'll give you a contact. And if you have a lot of money, then come and talk to me. So for sure we'll be able to do that for the moon, for the International Space Station. I think for Mars, technologically it's possible. And you ask for how long it takes. So to reach the moon, it's a couple of days, right? To reach Mars, you need to be, Mars goes 2 years around the sun, while we go in 1 year around the sun. So every about 2 years, we are on the same side. And then it's short. Short means 6 to 8 months to get there, right? When Mars is on the other side, it takes a lot longer. So we fly to Mars only every 2 years, 2020, 2022, 2024. So these are the years where you will see launches towards Mars. In the odd years, when Mars is on the other side of the sun, we don't launch. But 6 to 8 months. So if I don't know how long your holidays are, but it's a you know, we'll see. My guess is 20, 30 years. As soon as people, so as you know, there's an Artemis program at the moment running, Artemis 1, 2, 3. 1 did already fly, 2 is launching nowadays. So 1 was just sending no humans, but the right spacecraft towards the moon. Happened a few months ago. The second one is actually flying people to the moon, but not landing, going around, and that from 3 onwards, and then 4, 5, 6, etc. It's really landing on the moon. So that's NASA and ESA together. But in the same time, the Chinese announced that they would like to actually be on the moon, put people on the moon before 2030. So I think in the next 5, 6, 7 years, you'll see people again on the moon. The moment you're on the moon, because of prestige reasons, etc., you will have people who will send to Mars as well. So my guess is within 10, maximum 20 years, we will also start to colonize Mars. And we know from the International Space Station, we've had human presence in space for 20 years. So my guess is that we will really kind of colonize Mars in 10, 20 years and have then a permanent human presence on Mars for many, many, many years. And if you then want to look at good science fiction, you can watch The Expanse, which is one of my favorite science fiction shows, and see a little bit how that turns out. So that's tourism in space. Then your other question was accelerating humans to speed of light. At the moment, with the laws of physics that we know, if you accelerate a complex organisms like us to the speed of light, you're going to be torn apart, and that's it. So I actually don't know physiologically. Maybe anybody here is a doctor and can actually answer this, but I don't think you want to be accelerated to significantly faster than maybe 10% of the speed of light or so, and even that, I mean, you need to be accelerated gradually, of course. Otherwise, again, there's forces which will completely destroy you. So it's going to be very hard to escape our solar system within the known laws of physics. I think that's yeah. At the moment, we don't see that. And then the final question you had was, I forgot.
What will happen if you find life on another planet?
So there was, well, the quick answer is not much. Okay, I think we will tell everybody because we are chatty people, so we tend to actually be very proud of our discoveries. So nobody will keep it secret. There was, at some point, everybody who was searching for intelligent life in the universe, I'll come back and I'll talk about that another day, signed a protocol of what to do. And the agreement was if we see any sign of intelligent life out there, we keep quiet until we know whether we are food for them or prey or experiment or whatever. So and until you don't quite understand what you see, you just keep quiet. So that, and most of the groups who are actually searching for intelligent life out there signed the protocol. And then there are UN working groups, so from the United Nations, which actually follow other protocols, and there's a whole, yeah, so it's actually quite regulated. But for sure you will hear about it. But what you can hear tonight is we haven't found it yet, otherwise I would tell you.
Hi, hello. Yeah, I just wanted to ask you if there's, hi, hello.
Sorry.
I wanted to ask you if there's, you told us that there's a finite number of stars.
Mm-hmm.
So I was just wondering, that means that there's an end of the universe.
Yes.
So I was wondering what's after that. Is there like an empty space after that, after all those stars, or what's?
No. So
No?
that's a concept of space-time, which is it's not something that you usually think about for breakfast. So it's a little bit abstract. But the universe, it's a closed space, right? So imagine if you, so maybe the easiest quick analogy I could give you here in 10 seconds is if you were a little ant and you could only move on in 2D, you can't fly, and somebody would give you and tell you live on a balloon, on a football, okay? Then you would run around in circles and you would ask yourself, but you know, where does it end? Where does it start? Well, there's no end and there's no start. You're a little ant, you live on a ball and you run around in circles, and that's it. And if you take that in 11 or 12 dimensions, then that's maybe the universe, and we run around in circles inside these dimensions. So it's the space in which we live. It's the laws of physics of our universe. Can there be other universes beyond our universe? Yes, there can, maybe with completely different laws of physics, but at the moment we have no way of checking that. So we live in our universe. It is the dimensions we know, and typically the ones we feel are 4, yeah, 3 spatial dimensions and the temporal dimension. And then if you dig deeper into physics, then there might be actually supersymmetries and 11, 12 or so dimensions. And that's what we live in. They're closed, and what we experience in space-time, so 4 dimensions, is a closed universe. There's no end and there's no beginning and end. We know that temporally the time runs only in one direction. So there was a big bang, and since then we're expanding. But that's the answer.
Okay, thank you.
So,
thank you very much.
It's a bit abstract. I can recommend you some good books to read with lots of formula. But, I'm not sure that makes the concept simpler to understand.
Hi, good evening. Thank you very much for the speech and the class. I really want to ask about bacteria.
Mm-hmm.
Many people like me are concerned about bacteria, and what's about to bring materials into Earth containing bacteria? It could be virus, could be dangerous for people.
There are lots of things dangerous for people. And you live with 10 to the 14 bacteria inside you. And if you use an antibacterial or whatever, and you would get killed all these bacteria, you will die. You live in symbiosis with these bacteria. Now, so the question is more, if there's another life form on Mars or whatever, and we would bring it back intentionally or accidentally, then you can actually start to think about it. But it would need, if that life form is still alive, it evolved to adapt to Mars, to the best conditions on Mars. And when it would arrive on Earth, which the conditions are very different, that bacteria would not be well adapted to survive on Earth. So probably everything we bring back from elsewhere would die probably here. Or if it does not die, it does what life does everywhere else, is that the strongest survive. And the strongest is not, the strongest is the best adapted ones. And our life on Earth is so perfectly adapted to the life on Earth that they would probably outcompete any other organisms that we bring back. So I wouldn't be very concerned. And we're not going to bring back that many bacteria so quickly. So, and there are, I mean, for example, for the mission that I showed you for the Mars sample return, it's called, so which this NASA ESA mission, which we're bringing back samples from Mars in the mid-2030s. We're going to bring back samples together with the Japanese, with the JAXA space agency. It's a mission called Moon Mars Explorer. We're going to bring back dust from Phobos, which is one of the moons of Mars. That's going to be earlier in 2028. But there we have extremely careful protocols to completely seal these in containers. We have ultra clean rooms to open them, completely conceal, until we know whether there are living organisms in there or not. So for the things we bring back intentionally, there are very, very rigorous protocols these days to actually isolate it before we know what it is. But even if it got free, you know, life as we know it, the best adapted one wins. And if something evolved for 4 billion years on Earth, it will be better adapted than anything we can bring back from Mars.
Good evening. Excuse for my English. I would like to ask, most planets for the moment discovered are near from its star. I'd like to ask when we expect to discover the many planets like Earth at the same distance from a star like our sun. What it's matter of technology, it's matter of time. Thank you.
Time, okay. So it's true. So the two techniques I showed you to find planets, the one where the planet goes around the sun and the sun moves, this is easier to detect if the planet is very close to the sun, because then it goes away in a few days, and then you can make this measurement in a few days, and you don't have to wait for 1 year if the wobble is very slow, or 10 years if it's a Jupiter. So at the beginning, we were finding a lot more planets very close to the star, and these planets are extremely hot, and they're not suited for life. But this completely changed about 5-6 years ago with a Kepler mission, when they started to actually detect a lot more planets with a second method, with a method where the shadow crosses the star, because that is not biased towards, or not that biased towards planets which are that close. And we build on these techniques, and one of the satellites I showed you, which is called Plato, which we are launching in 2027, so in 4 years from now, this is specialized to find exactly Earth-like planets at an Earth distance from normal stars. So, and so you have to wait for 4 more years, and then we're going to observe with the Plato mission a lot. I mean, lot means tens, hundreds of these planets which are in habitable zones. And already now we know hundreds of planets in habitable zones. So we have a lot of candidates for where we can look for life already. We just need to increase the sensitivity of this, the measurement of the atmosphere, the composition of the atmosphere. That is where our telescopes are not quite sensitive yet. So the big ones I showed you will be. So you wait another 5 to 10 years, and then we have the sensitivity to really study the atmosphere as well. But planets in habitable zones, we know now hundreds. Yeah.
Hi. I would love to hear a bit more about the thought process behind which missions actually get to fly, because like with the JUICE mission, obviously there is crazy timelines involved. I imagine if it takes 7 years to Jupiter, it probably takes a lot of time to prepare. Or like the sample return, you need to coordinate that. I assume that's not some small brainstorming group at ESA. Like, how do you figure out what would be interesting to check out in 20 years?
So how most of the space agencies work. So first, I'll give you a short answer on what is the lifetime of such a space mission. So typically there's about 10 years of technological development, because we need to actually develop all kind of new technologies to actually really put onto the spacecraft. Then you build the spacecraft, which takes another 10 years. And then you have the launch, and then maybe interstellar travel, or the length of things. So typically, one of these, what we call missions, lasts about 30 years from the beginning to the end. So very often what we do at the space agency is we don't build for ourselves, we build for our children, right? So what we fly, the missions we fly at the moment were done by the generation of my parents. And what I'm preparing now is actually for the generation of my children. And so we think about these timescales, which compared to astrobiologically is super short, but we always think one generation at least ahead. So that's our job. We don't do anything for us. We do it always for our children, as our parents did for us. So in the space agency parents. So that's one. And then who decides? It's not just us sitting in a corner saying like, hey, I love Jupiter. I prefer Saturn. Let's go to Saturn. So we go out and in the case of the European Space Agency, there are 22 countries in Europe which contribute. And so we have every 10 years, we go out and we invite everybody to bring ideas and let them decide what the big themes are, okay? And they're going to say, okay, we need to do more planetary science. We need to fly to Titan and look for life on Titan, etc. And they give us the ideas and they give us the concepts, and then we go and we develop the technology to make it happen. So it's not us deciding, it's really the community that we serve. So it's typically hundreds, if not thousands of scientists involved into deciding what to do next. And then we have a pipeline, so we prepare. So typically we launch one of these, the European Space Agency launches one of these science missions every 2 years or so. So we are constantly in this pipeline of preparing missions. So they last 30 years, but every 2 years we start a new one. So we have an entire fleet and armada. And my kids call me Darth Vader because I'm in charge of a large fleet of spacecraft in the solar system. And that's what we are, and we keep putting more in, and some die, and so on. And and we do the legacy for our children then afterwards. With your tax money, by the way. So thank you.
Okay, I have a question regarding the samples that you expect to get back to Earth in 10 years or so. My question is if those samples may contain ice from close to the surface. I don't know if that could happen. And considering that in the past Mars had periods of more dense atmosphere and liquid water, maybe if life evolved in the past, you may find some life forms frozen on the ice. Is that feasible? Could it happen?
Yes and no. So in fact, I told you we have a satellite, we have actually multiple satellites, but some of them going around Mars since 20 years. So we know Mars with a resolution of meters, we know exactly where ice is, etc. The limit for bringing back the samples we want to bring back in 2030 is that at the moment, the Perseverance rovers can only take the surface of of Mars and return that sample. The rover we have prepared, we would like to send to Mars, but we had this problem. It was supposed to actually fly together with a Russian mission, and Russia invaded Ukraine, and so the rover is now in Italy and is waiting for the next taxi to Mars. It's a different story. So that one will drill deeper into the soil of Mars. So we're trying to actually really get to meters. We're trying to develop more and more rovers which can actually go deeper and deeper into the soil of Mars to actually really get deeper probes. At the moment, we can only bring back the surface of Mars. So what we did with the geologists, so we have teams of geologists working in our agencies, they actually looked at where the oldest rocks are on Mars, and we are trying to actually take the oldest rocks back to Earth. So same thing actually that you do, because if you think about how do we know that there was life on Earth 4 billion years ago? Say, oh yeah, I just go and pick a rock which is 4 billion years old. Okay, so where do you find a rock which is 4 billion years old? If you have plate tectonics, most of the surface of Earth was destroyed many, many times before that. So you have to go to the oldest places on Earth, which are Australia, Greenland, etc., to find very old rock. And in that very old rock, you can look for fossils, chemical fossils or actually physical fossils. And we try to do exactly the same on Mars. So we have studied Mars all over. We know exactly the geology of Mars. We know which areas of Mars are how old. Some are as old as our Earth, obviously. And that's where we landed our rover, and that's where we're actually taking the samples that we want to bring back, so that we have a hope that in the crust, in the upper layer of the soil, we can bring something back. It's not as deep as the ice where that you're mentioning. And also the ice is cold, but it's not very cold. I mean, so the cold means minus 150 degrees. Not cold enough to actually keep anything, any organism hibernating or so. So, yeah. And the surface, as Mars as well, has a surface which is renewed all the way. Although Mars doesn't have plate tectonics, as Mars is.
Thank you very much for your presentation, Marcus. My question will be: you said that
Okay, sorry.
Probably within the next 2 decades, we'll be on Mars, as you said. What will be like a regular? Do you think it's possible to have like a regular human day-to-day life on Mars on a medium and long term? And what will be like the difficulties of being there on a long term?
I think the difficulty is just the distance that you need to resupply it. But de facto, you could take the International Space Station, which has just a few floating containers, or actually the Chinese space station, which at the moment has already 3 modules, and they have a permanent presence also there. So you have actually 2 places in orbit which have permanent presence of humans at the moment. And these are just containers. And we know that we can transport these containers to Mars, put them on Mars, and then there's no technologies that we need to develop. You just need to actually resupply them regularly. And that the distance then, you can only fly there every 2 years. It takes you 6 months to go. So you need actually a constant chain of launches that bring material to Mars, which 5 or 6 or 7 years ago, when we had launches, maybe only 10 launches of rockets per space agency per year, that looked difficult. Now this year, for example, SpaceX is going to launch 100 Falcon 9s. Right? So they launch a rocket every 3 days. So we are now in a completely industrial way of launching rockets. And when you start doing that, you can actually just in a year where you can go to Mars, you launch 100 rockets towards Mars, and you just bring everything you need to bring for the next 2 years to Mars. So I don't think that there's a technological hurdle to do it. It's expensive. You need to develop a few things and think a little bit differently on how you're going to sustain people there. But it's easy. Okay, so there's no crazy technology that we need to actually colonize Mars. You need to bring a lot of material to actually then build over there or assemble over there a rocket to come back. Okay? So most people will go to Mars first, will go and die on Mars. But the way Europeans colonized part of the other continents 500 years ago was also one-way trips. Nobody in the crew of Magellan thought that they would actually necessarily buy a return ticket. They were just going one way. Some of them came back, most of them not. In the same spirit, you could actually just start colonizing Mars now. That's my view of things. Not everybody would buy a one-way ticket, and I would not. So, but I think some people would.
Okay, thank you, Margus. There is a last question from our YouTube channel. There is a possibility of finding life without liquid water. I mean, is there any research about that?
Okay, so that could life not based on water exist? And that goes back to the beginning of my talk. We know only of one form of life. So I could say like, of course, but I have no idea. I know only the one life form we know is based on water. Now, if you actually work through the definition of life, we just want to actually use energy to produce something, typically copies of yourself, and you want to actually have evolution there. And you look at what type of chemistry you would use. So water is a fantastic molecule because it's a so-called polar molecule. So you can actually easily assemble, disassemble, etc. And it can break big chemical molecules. So water is very nice, but it's not unthinkable that you could actually have some other medium which would actually be as efficient for doing this chemistry that you need to actually have life, this complex chemistry. And I talked a little bit about Titan. So Titan is far out. So it's a moon of Saturn. It's far out from the sun. It's very cold there. So water is not useful because water would be ice. But methane and ethane are liquid. Also, our chemistry is based on carbon chemistry. So you have carbon atoms. Carbon atoms have 4 free electrons. You have 4 bonds, and they are very actually strong bonds. If you're in a cold environment where the temperatures is lower, then this chemistry is harder to actually break, reassemble, which is what life is doing. So you could go to an easier element, and if you remember the periodic table of elements, an element which has exactly the same property is always the element which is just below. And just below carbon, you have silicon. So you can actually take silicon. Silicon has 4 free electrons. You have 4 bonds as well, so you can actually do the same kind of chemistry, but the bonds are weaker. So it works better at colder temperatures. So when if you're a fan of the Alien movies, the Silicon Life, this is not actually crazy. It's actually carbon chemistry as we are, but better adapted to cold temperatures would be silicon chemistry. Then you would use another solvent, not water, but something else, and so on. So you can start spinning around based on what we know life is today, what different forms are. And you can go to weirder and weirder systems. Again, it would be a 1 hour, I think it's a 2-hour lecture that I usually have on that topic. DNA, do you need DNA, which is a double helix? Could you go to something simpler, which is RNA? So a single helix. Now we use this in our RNA. You have always 3 bases which code 1 amino acid, then the next 1 amino acid, and the next amino acid to form a protein. But could you use with 2 bases? What would happen if you had 4 bases? Do we need 20 amino acids to form proteins? Could you do life as complex as the life we know if you didn't have 20 amino acids but just 10? What if you would use the 100 amino acids that we know that exist, or over 100 in our universe? You would make super complex life. So you can spin a lot of these ideas around, and they're great, and the students love that, and they're all prepared to actually search for the weirdest life possible. But we have found only one, the one on Earth, and that's why we actually would love to find just a second type of life to actually better understand what life really is, and then answer all these questions. Can it be without water? Can it be based on something else than carbon chemistry? Can we actually use other elements, etc.?
Okay, Marcus, thank you very much. I'm sure that you will be back here to give us some more lectures about
intelligent life.
Whatever you like. Intelligent life?
Let's search for intelligent
What's
life next
about?
time. That's always fun.
Okay.
There's none in the universe.
Thank you very much. Muchísimas gracias.
Thank you very much. Thank you. It was a pleasure.
Gracias, Marcos. Voy a aprovechar para comentaros que, aunque todavía no está anunciado, el día 24 de junio va a venir la Deputy Manager de la NASA, aquí que ha sido astronauta de NASA. Bueno, una de las principales astronautas de la NASA va a quedar una conferencia el sábado 24. O sea que sois los primeros que lo sabéis, los primeros que os podréis apuntar si queréis cuando mañana o pasado salga el anuncio. ¿Vale? Será una conferencia sobre, bueno, también espacio y qué nos espera en el futuro el espacio. Gracias, Marcus. Bienvenido.